Syzygy episode 62, The Cosmic Sponge. And welcome back for another edition of the Syzygy podcast. My name is Chris Stewart. I'm sitting around the round table in her office from Emily Brunston. Hi, Emily.
Hello, hello.
So today we're going to be talking about, well, I was about to say big things, but the biggest thing that there is. We're going to be talking about the size of the universe, the large-scale structure of the universe. We thought we'd tackle that one today. It's been on the whiteboard here in Emily's office for a while. We should talk about that, and we finally got around to it. Emily, big stuff today.
Yes, the largest stuff.
Yeah, which is really interesting because you kind of think, I don't know, naively in the back of my mind, and I do have a lot of naive things in the back of my mind as we're discovering as this podcast goes on. Naively in the back of my mind, there was always this picture of, well, you've got, the solar system, and then you stretch out and you've got the galaxy, and I know that we've got clumps of galaxies and so on. But then my visualization of the large-scale structure of the universe kind of ends there, and I just imagine, dotted throughout the universe, these clusters of galaxies. But it's much more interesting and complicated than that. So we'll be chatting about that today. But before we do, Emily, a couple of things in the news this week, including we've named a new robot for Mars.
Yes, this is always the exciting bit. I mean, we could have named it Marsy McMarsface.
We could have, and given recent internet history in that regard, that would probably, you would have put a bit of money on that. But no, we haven't gone that way. What have we got instead?
So this is a new NASA rover that's going to Mars. It's going to be called Perseverance, which is nice. I mean, it's sort of,
I'm not getting a lot of excitement about the name from you here.
Well, it follows on from, you had spirit and opportunity, now curiosity. These are nice words that...
Yeah, and they're all good traits that a robot on Mars should have. They should have spirit. They should be going out and taking advantage of opportunities, and perseverance, surely. Is a good thing to have
it's
in
good.
a robot.
I mean, it is good, but...
You don't want to give up at the first rock. It's like, I just can't be bothered.
Yeah, but that's never been a problem, really, for Mars rovers, has it? I mean, we haven't had a lot of strikes on Mars.
True. Come on, persevere, little robot. No, don't want to.
It does kind of sound like we've found things a lot more difficult than perhaps it should have.
Right. I guess I hear what you're saying there. So were there any other contenders that you would have gone for? You going to go
I
out on a
haven't
limb?
seen the full list, but it's nice. I think I'll get used to it.
It'll do.
Yeah.
Yeah. See, I kind of like it. There's something about it which sort of, particularly in this day and age.
Well, maybe that's a reflection of why
I feel a bit like
works.
in 2020, perseverance is a good thing to call a robot that we're using to explore. No, we can do this. Come on, persevere. Don't give up. Humanity, whatever you're facing, don't give up. Persevere. So I think we can all take something from that. What else is in the news this week?
So another thing that I picked up that was quite interesting was we're looking at, can we put together, and this is just still an open question, a new mission that will go to Uranus.
Okay. Now, why is this come up now?
So, well, it turns out that we're a little bit of scrambling. We're a little bit behind on this because there's a very important alignment of the outer planets, which to get to, we would have to launch a mission in 2031.
Okay. Now, that sounds like a long way away. That's still, a decade plus a little bit away. So we've got tons of time, right?
Well, it turns out that you kind of need about 2 decades to plan these missions properly, right?
Okay. So to actually be able to launch and take advantage of this particular lining up of the planets in the right way. Because we talked about this before, that you can't just, we're going to go to Neptune or something, and we're going to just go there. You've actually got to, we need to swing by this planet first, and then we need to swing by that and get out there at the right speed, at the right time, with the right amount of energy, rather than taking all of that fuel yourself.
Yeah.
And so you've got to look for these alignments of the planets in order to make a mission viable, right?
Yeah.
And so that's what's happening.
You really need Jupiter in this case, right?
Right.
So Jupiter's big mass and it helps you get out there. So for this, there's 2 alignments. There's sort of one you could go to Neptune and one you could go to Uranus. I think the Uranus one is more likely because it leaves kind of a year later.
Right.
So we've got a little bit more time to prepare that.
So I'm guessing that it's not so much that the astronomers didn't know that this was going to happen so much as there's a heck of a lot going on and maybe budgets have been tight and suddenly they find themselves in a position where, look, we could take advantage of this, but we really ought to have started 10 years ago.
Yeah. So I think, well, there's a lot of new science that we want to do with these outer ice giants because we don't know a lot about. I mean, we haven't been to them since the Voyagers flybys.
Yeah,
and
that's
things.
true,
So,
actually.
you know, they're really mysterious. We don't know a lot about them, and
technology's moved on. Like, we could learn so much more now.
Indeed, and we're in a position where we know lots about exoplanets, and finding out more about the ice giants in our solar system will help us understand more about exoplanets as well.
So, scrambling, is this NASA?
I think
ESA?
the feeling is that NASA might not be able to do it all alone because
Right.
of the time constraints. Maybe if ESA gets on board and they can sort of join forces, then it's
But
possible.
scrambling at this point.
Yeah.
They're under a time pressure. We've got to get this thing done.
So I think there'll be some proposals for upcoming fundings for sort of medium-sized missions or even big missions. So we'll just have to see what comes out of that. But this is the amazing thing. So if you're on the edge of your seat thinking, when are we going to get these new pictures, this new information about these planets? Well, even if we launch in 2031, the spacecraft won't get to Jupiter until 2036.
5 years just to get to Jupiter.
That's Jupiter. It won't get to Uranus until 2043.
Space is big, isn't it? 2043.
Yeah.
Wow.
So do you put that in your calendar now?
Astronomy is weird, and space exploration's weird, right? That we're talking 11 years out from the earliest possible, or the appropriate launch date, 2031. We're 11 years out from that. Where, what did you say, 2043?
Yeah.
So that would be another 12 years beyond that before you'd even get there. And we're already 10 years too late, really, to be starting to think about this. Like, this is not short-term thinking.
Yeah.
This is long-term. The people working on it now might even be dead by the time it happens.
Well, this is what happens. You dedicate your full career to a particular mission.
Wow.
Quite often. Yeah.
It's amazing it happens at all. Anyway, so that's the news for this week. But let's get on to the topic du jour, which is big. The universe. The universe at its largest scales. And as I sort of said in my little sort of personally revealing intro, that I never really thought terribly much about the large-scale structure of the universe. I just imagined it was sort of, clusters of galaxies going all the way out. But it turns out that it is much more interesting than that. So maybe we should begin with how big is the universe? How do we even think about large-scale structures of the universe? What are we talking about?
All right. So we have, so the universe is a thing that we live in, right?
Yes. Yeah.
Let's start with that.
Yeah.
Now, it has a size, and usually what we talk about when we talk about the size of the universe is the size of the observable universe.
Right. I mean, jury's still out on some of these concepts, but aren't we fairly conclusively happy with the notion that the universe is infinite?
Well, Mayo, no.
No?
It might be finite but unbounded is another option.
Maths is weird.
Yeah. So, a slightly analogy to that would be you can have a sphere. If this is in 2 dimensions, you can have a sphere that you live on, whereby the surface area of the sphere is finite, but it's unbounded in that if you carry on in one particular direction, you will eventually get back to where you started.
Right. Like if I started walking from here, from your office, going in a particular direction, I would go all the way around the Earth, on a grand circle around the Earth, right? And ultimately come back to where I started from and go, oh, that was odd. I thought I was going forever. And it turns out I'm back where I started from. Finite surface area, but it's unbounded in that you don't come to a wall.
Yeah.
You don't come to an end. You just keep going. You get back
You
to where
look
you
back
go.
on yourself, yeah.
The equivalent in the universe would be, I'm going to go in this direction, up into space, past galaxies, past clusters, just go. And eventually, hang on, this is looking familiar. I'm back where I started from, which warps your mind. You haven't gone around a surface in the sense that we know it, but in 4 dimensions, you kind of have gone around a surface. It could be a finite amount of universe, but there's no end to it. You just strangely come back to where you started from.
So that's possible.
Yeah. We don't look up into the night sky and see copies of ourselves going on, like in that room where you got mirrors facing each other. So I'm guessing if the universe is finite and unbounded, it's on scales unimaginable. So let's back away from that idea a little bit and talk about the observable universe. How big can we see?
Yeah, so what we call the observable universe is the amount of space, or the volume of space, if you like, where we get information from. So this means that information travels fastest in terms of the speed of light. So let's say light is traveling towards us from the most distant parts of the universe. And now it turns out that the speed of light is finite. So, you can't break the speed of light. And when you're traveling as a photon, you are traveling at the speed of light.
That's as fast as you can go.
And we also have another finite thing, which is the age of the universe. So the universe has been around for something like 13.8 billion years.
Yeah, at best guess. You work it backwards and that's the Big Bang, 13.8 billion years. But it's not as simple. Like the naive view of that would be, okay, so that means that the furthest we could see would be something where light's been traveling to us from the furthest side of the universe for 13.8 billion years. So the observable universe must be 13.8 billion years across. In radius, distant from us. That would be a naive view.
And it's actually a really common misconception with the universe.
Understandable,
because
but wrong.
We talk a lot about light years and how a light year is the distance that light travels in 1 year.
Sure, hence the name.
If light has only been traveling for 13.8 billion years, then that must therefore mean that the universe is 13.8 billion light years across.
Seems reasonable.
It's true that the photons that we see, the light that we see today from the most distant part of the universe, has been traveling for 13.8 billion years. That is true. What's not true is that the distance between us and where that photon came from is 13.8 billion light years.
Okay, now hang on a second. Hang on. Because if light travels at a particular speed of light, and it's been going for 13.8 billion years, how could the distance not be 13.8 billion light years? It just seems self-evidently, by definition, that's surely the answer. So what are we missing?
Well, the universe has expanded in this time.
It's had 13.8 billion years of expansion along the way.
Yeah.
Right.
So one way to imagine this would be the piece of light has left your very, very distant object and it started traveling towards us, and then the space behind it has expanded. Well, the space in front of it has as well. But if you imagine the space behind it has expanded, then that's taken that object further away from us than it was when the photon was emitted. Right.
Okay. So even though the light, there's no getting around the amount of time, the number of years that the light has been coming to us, the space is the thing that changes this calculation, that the space itself is expanding.
Yeah.
And so the distances are much, much further. How much further?
So we're now looking at that particular photon has traveled, well, the object that photon came from is now 46.6 billion light years
So
away.
You're now talking about the furthest things away that we could conceivably get a photon from is how many?
46.6 billion.
That's quite a stretch then. Like the universe is expanding quite a lot over those billions of years.
Yeah, we're not kidding with cosmic expansion.
Yeah, this is not mucking around. And over, that's the thing about cosmic expansions, that over very small scales, like the scale of this room or even the solar system, even the galaxy, you don't really see it. But over very, very large distances, like across the universe, that's where it really builds up. And particularly over very large distances, over very large timescales, suddenly that's a lot of expansion.
Yeah, it is.
Yeah.
And it's still going on, of course. So the universe is still expanding. So one interesting factoid, if you like, is that if a photon leaves an object today, if that object is more than 60 million light years away, which is not super far.
No, we were talking about 40-something billion. So we're now talking
60 million.
60 million, which is not very far.
If that object is more than 60 million light years, that photon will never reach us.
Wow. So if it leaves today,
yeah.
Wow. Okay. And that's because the universe is still expanding. And so over that 60 million years that it would naively take to reach us, the universe will have expanded so much that actually it's just not going to get to us. It's never going to get there. Wow. I hadn't realized that scale was so small.
Exactly.
Cosmically speaking.
It's interesting. So when we do talk about a lot how when you look into the deep depths of the universe, you're looking back in time because you're looking at photons that were emitted that many billion years ago.
Cosmology really messes with your concept of now, doesn't it?
It really does.
It's really, really weird. Okay, so that's a sense of the size of the observable universe, right? So we're going to sort of put a big sphere around us of 40-something billion light years, which is big.
It is big.
That's big. Okay. Can you give us a sense of how big? I mean, how do we get a sense of that? Like, there's a big number.
It is a big number. So I guess what we're going to be talking about is kind of the distribution of particularly galaxies, in this case, in that sphere, in that size of the universe. And so kind of the biggest structures that we see in the universe, to give that some context, are about 1 billion light years across.
Okay, so we're talking an observable universe in the 40 billions, structures within that of 1 billion or so light years. So these are big things. What are those structures?
So let's talk about actually what on earth is this large scale structure anyway? Yeah. This is all quite an interesting and new concept for cosmology and astrophysics, because if you dial the clock back to not very long ago, I mean the 1970s, we started measuring the distances to galaxies pretty accurately. And in the 1970s, we had the distance to maybe kind of about 1,000 galaxies. And that didn't really tell us a lot about large-scale structure.
No, I mean, there are a lot of galaxies out there. And 1,000 isn't terribly many. It's a good start, but it's not terribly many. Can you, when I asked a minute ago, this sphere, 40 billion light years radius, do we have any sense, like, what's the estimate on, like, how much stuff is in there? How many galaxies do we think are out there? Like, ballpark
Yeah, I mean,
figure.
we don't know exactly, but we're thinking maybe on the order of 100 billion.
100 billion. So, you can sort of, I don't know, I'll use as the mnemonic, there are in the order of hundreds of billions of stars in our galaxy, 100 billion galaxies in the observable universe. Okay, so I'll lock that one away. Yeah. So hundreds of billions. And we knew the distance to about 1,000 of them, which is, it's a start.
Yeah, but now since then, of course, we've upgraded all our telescopes. We've been able to make fantastic measurements of lots of galaxies. We have pretty good distances to about 1 million galaxies now.
Okay, so it's getting better.
That's quite a lot, actually.
Yeah.
And so that's enough to start to say, well, how are they distributed? Are they evenly distributed? Do you have like kind of roughly the same distance between each galaxy or each galaxy cluster? Or does it turn out there's some kind of larger scale of structure? Do galaxies form into different organizations, if you like?
Yeah. I mean, are they just sort of uniformly spread, or do they tend to clump together? Because we know that things across different scales of the universe do clump. You know, we're a clump, and the solar system is a clump, and the galaxy is a clump, and the galaxy's got other clumps within it. There are arms and so on. And then there are clumps of galaxies. There are groups of galaxies. Does that clumping keep going?
It does. So let's step out using ourselves as an example, right?
Okay.
So the Milky Way galaxy, our galaxy, is part of what we call the local group. Mm-hmm. So it's a group of galaxies, meaning it's kind of a small collection, maybe 100 or so galaxies. And then we are also part of a cluster, or supercluster really, but you can have a cluster of galaxies that's maybe kind of 1,000, and then you can have superclusters where you're looking at tens of thousands of galaxies plus.
And these are groupings based around their gravitational interaction over large scales. That it's not just, there's a bunch of galaxies which are all roughly in the same part of the sky, so we'll call that a group. In the sense that a constellation is a group of stars, but only because we happen to link them in our brains looking at the sky, right? A constellation is not...
It's not actually... Well, sometimes it is, but
sometimes it can
not very often.
But generally it's not. Yeah. But what you're talking about, these groupings, these clusters and superclusters of galaxies, these galaxies are actually influencing each other, forming that, and that's what forms the group. That's what makes the group.
Yeah. So as an example, in our particular case, our local group is kind of on the edge. We're in the backwaters, if you like, of a local supercluster, which was only really kind of nailed down about 2014, and it's called Laniakea. And it's a supercluster, which is, the Virgo supercluster, for example, forms part of this. And what, if you like, draws the boundary of what we decide meets the criteria to be in the supercluster is, do you have some kind of motion towards what we call the Great Attractor?
Oh, that's a good name.
We've got some good names in this episode.
Local group, not such a good name. It's a bit dull, but what was it?
The Great Attractor.
The Great Attractor.
Yeah.
What's the Great Attractor?
So the Great Attractor is a kind of a bit of the universe. We've got some observations, but the problem is that the Great Attractor sits in a place of the universe we call the zone of avoidance.
This is starting to sound like something from a Dungeons and Dragons game or something.
Yeah, it's
What?
great, isn't it?
The Great Attractor in the zone of avoidance.
Well, the zone of avoidance basically means that if we sit in the plane of our own galaxy,
Yeah.
so when we look at the night sky, you see the plane of the Milky Way. That is beautiful, and we appreciate that. But it's a pain if you want to look at galaxies that are beyond, that are
Right.
kind of behind that.
Yeah, if you've got to look through the entirety of the galaxy to see beyond it, that's hard.
Yeah.
I mean, I would have thought impossible, but, what do I know?
You can do it in some wavelengths. So the problem is that this attractor does lie in the zone of avoidance. Just coincidentally, it happens to be.
And so the zone of
Difficult to
avoidance is
observe.
just avoid trying to observe in this part of the sky. Is that what
Yeah,
that means?
exactly, yeah.
So it's not a part of the universe where, things avoided, stay away from here. It's that we can't see there.
Yeah,
Right, okay.
basically. Avoid putting your optical
Yes,
telescope there if you
gotcha.
want to see some galaxies.
Gotcha.
So we probably think that it's a piece of the universe where it's got maybe a few thousands of the mass of the Milky Way in a fairly condensed region, which makes it attractive gravitationally. So all the galaxies that are part of this supercluster have some kind of flow towards this great attractor.
Right. So in some way, it's kind of like a bit of a hub for this large group of galaxies.
Yeah, so
Right.
they've probably got some sort of clustering of big things towards the center, and that enormous clustering of more mass is drawing in all the other clusters and so on
Right.
towards it.
Okay. And so you were saying that we here in the Milky Way, we're kind of on the outer backwaters of that, but we seem to be within this larger scale sort of supercluster around the Great Attractor.
Yeah.
Yeah.
You can think about it like a kind of a basin, a sink,
Okay.
so that everything that you put inside the actual curved part of the sink is going to eventually roll towards the plug. this
Right.
hole, right?
Gotcha.
So-
To be clear, there is no plug hole. We're not going to disappear
no,
down
no.
it. That's, yeah.
Yeah,
that-
but
that's
it just looks like we're all moving
Yeah.
towards that direction.
Okay.
So that's where we sit. Now, to give you a sense of scale, that's probably something like 150 million light years across.
that's this supercluster.
Yeah.
150 million. Okay.
Or maybe the Great Attractor is somewhere between 150 and 250 million.
But it's in the
light
hundreds
years,
of
yeah.
millions of light years. Okay.
Yeah, so it's
getting pretty big.
That's our place in the universe. Now, that's only sort of one part of what we're talking about. If we were to look at lots of other superclusters, lots of other groupings of galaxies that are much, much further away than that, then we can, if you just map, this is one of the most basic things we want to do in astronomy is map the universe, right?
Right.
I mean, my first year lecture course is called Mapping the Universe because it's all about laying down the foundations of how do we know about the universe that we live in.
Yeah. Where are things?
Yeah.
Yeah. We see things. Where are they?
Yeah, and how do you figure out where they are?
Yeah.
Which is
yeah.
quite
That's,
tricky.
that's most of the problem, really.
Yeah. So if you were to map our universe, then you mapped kind of the individual location of all these million galaxies. Then you end up with a picture. Let's say you've got your map that looks kind of interesting. It looks like things are not uniformly distributed, but things are forming groupings which we call filaments or walls. And also between those filaments and walls are voids.
So I'm guessing from the terminology here, a filament is sort of a long string of stuff. A wall is kind of a sheet of stuff, as opposed to just filling an entire volume filled with stuff. It's forming into these structures. You're seeing it come out. And then in between those, there are voids where there's not much stuff.
Yeah, so when you put this into 3 dimensions, it's kind of a little bit like a sponge.
Yeah, I've seen some of the pictures of this, and whether that, I can't remember off the top of my head whether that was from simulations or whether it was from data or both. But yeah, it's very spongy.
Yeah, or sometimes they call it the cosmic foam or the cosmic web.
So what's going on there? I mean, you were talking about superclusters and the Great Attractor, and so I'm imagining this gravitational influence across all of these galaxies going, let's clump like this. What's going on to form filaments and walls and voids?
Well, this tells us something about actually the whole evolution of our universe, because there must be something that's telling the galaxies to form in these ways, to form along these structures. Now, if you took a very basic model of cosmology and just said, okay, we're going to have Big Bang, then we've got some other observables that we've seen. One of them is the cosmic microwave background. We talked about that in episode 41, if you want to rewind to that one.
Go back and have a listen, all the details.
But we've got some evidence of what the early universe was like, and then if you want to say, well, that's what the universe was like in the early parts, now it looks like what we see today, then you can build up a model of cosmology based on those observations. And the interesting thing is that if you just take Big Bang, boom, now form galaxies, they don't form these kind of structures, and they certainly don't form them fast enough to have the universe that we see around us today, unless you put in a very special ingredient into your models.
Which is what?
Which is dark matter.
It all comes back to dark matter, doesn't it?
Yeah, it really does. Because when you look at the very early part of the universe, and if you want to form structure out of this kind of, it's almost uniform. The light matter, the stuff that we know about, the protons, the neutrons, the electrons, and therefore the stars and so on.
Yeah, the stuff that we call stuff.
Yeah, that's all very, very smoothly distributed in the very early part of the universe. So if you want to make galaxies and therefore stars, etc., then you've got to clump this stuff. And it turns out you've got to clump it really, really quickly, because we see the earliest galaxies form very, very early on in the universe. And to get that to clump as quickly as it's clumped, you need something else underneath, something that has gravity that sits underneath all of that normal matter that has caused that structure to clump.
So in your models, you're sort of looking at, okay, so here is Big Bang, early stages of the universe. We expect it was like this, and we have evidence that says it looks like this. And then march it forward, and we need to inject this other thing. And let's call it, for the sake of an argument, dark matter. We need to put that into the model in order for things to then evolve to be what we see now, to be these large-scale structures. The only way that's going to happen, or are you saying even the smaller scale structures, like galaxies forming when we saw them form, you need to have that dark matter?
You need a bit of both, yeah. So,
right.
So you need this dark matter to have, you can ask, well, where did the dark matter structure come from? Because that had to kind of exist as well.
Sure. I mean, if you're just pushing the problem further out, aren't you?
Yeah.
It's like, okay, fine, dark matter. Where is that structure?
So the structure of the dark matter that we see comes from, this is one of my favourites, I just wrote this verbatim from where I was reading it, quantum fluctuations in the early universe.
Oh, of course. So not only are we injecting the dark matter, but now we've got quantum to deal with as well.
But I always love it when quantum turns out to be the answer, because it turned out to be the answer of just, the basic why is the sun shine. You need quantum mechanics to understand that. And it turns out you need quantum mechanics, the things that happen on the tiniest scales in the entire universe, to explain the largest scales in the entire universe.
If that's true, then that is utterly nuts, because, as you say, like quantum, we don't see quantum that much around us on a day-to-day basis. It is there if you look hard enough, but it's all about stuff that's happening down at the atomic level or smaller, right? It's about how the tiniest things work. That's where you really see the effects of it. But of course, if you go right back to earliest epochs of the universe, Big Bang, that's what it was like. The universe came from, as far as we can tell, this incredibly dense, small, ludicrously quantum universe. And so those effects were there. What you're telling me is that the quantum fluctuations, right? Quantum is a very sort of wibbly-wobbly statistical thing. Quantum fluctuations, tiny little quantum wobbles, would have been blown up to the largest scales of the universe. And that's why we see the filaments and walls and things that we see now.
Yeah, isn't it amazing?
That is bonkers.
I love it.
Really nice.
Really, really love it. So, going back to what we can actually observe around us today, I've sort of talked about mapping the positions of all these galaxies. And this is not as easy as perhaps I glossed over and said it is. Because
it's easy. Piece of cake. We just do this.
Just, measure a few million galaxies, please. And so it's worth just having a quick foray into some of these amazing observations that have taken place over the last couple of decades. So how you measure the distances to really, really distant galaxies is generally by measuring their redshifts. So what we're doing here is we're saying, okay, the universe is expanding. And we know that the farther away galaxies, the further away a galaxy is, the faster it's moving away from us because of that expansion.
Yeah.
And if you've got an object that's moving away from you, then the light from it gets redshifted by the Doppler effect. And so it becomes a bit redder than it should be. And you can measure this redshift for a particular galaxy, and you can say, okay, so now we measured the redshift, we can then backtrack that and calculate the distance.
Right. You're using the fact that things moving away from us look redder to go, okay, if this looks redder, then it is moving away from us, and you can figure out how fast it's going away by the redshift.
Yeah.
And that tells you how far away.
Yeah.
Because of the expansion of the universe.
And we don't just kind of look at a galaxy and say, well, that's quite red, so maybe that's quite far away.
Yeah.
You've got to make a pretty precise measurement
There
of
are
that.
numbers involved.
Yeah. And usually we use hydrogen as kind of a marker point, and we sort of say, okay, well, if hydrogen's the lines of hydrogen that we see in a spectrum have been moved away, been redshifted by this much, then that's kind of our measurement.
Yeah, because that's using I mean, we've talked about this before, but it's using the fact that every element, every molecule has its own sort of fingerprint signature of its spectrum, that it absorbs and emits radiation, light, at very specific wavelengths. And so when you say, you're looking at hydrogen observing hydrogen in a faraway galaxy, you're looking at those particular wavelengths of light coming from the galaxy. Oh, that's hydrogen at that particular wavelength. Or at least it should be hydrogen, except the numbers are wrong. It's like kind of shifted down far more into the red than it would be, but we know it's hydrogen. So we work that backwards and go, well, then it must be this moving this quickly, so it's this far away.
Yeah.
And you can get that pretty accurately.
Yeah, you can. The problem is it's kind of painstaking to do because spectroscopy is kind of a bit more complicated to do than photometry. So just measuring the brightness of an object is fairly straightforward.
Yeah.
Whereas taking a whole spectrum and breaking up that light into all its different colors is a bit more complicated.
Well, I can imagine because, I mean, there isn't just hydrogen. There's loads of things. And if they're all shifted, then all of those different spectra, all of those different fingerprints are all smudged over the top of each other. And actually figuring out what goes where must be kind of complex.
Yeah, and the worst part of it is that takes a while to get a good spectrum of an individual galaxy, let's say. And then you're going to say, well, can you just do it for a million different galaxies?
Yes, please. Yeah, when you're done with that one, move on to the next one and then repeat.
So in the early 2000s, we kind of came around the kind of technology that we needed to be able to do this on large scales. Mm-hmm. So the first really famous big large-scale survey of this was called 2DF.
Ah, yes, I've heard of 2DF.
So 2DF stands for 2-degree field. So they took a 2-degree field of view and took lots of exposures. And what they did was instead of looking at each kind of galaxy individually, they were looking at dozens at a time using a really cool technique using optical fibers.
When you say 2 degrees, like that's 2 degrees across the sky?
Yeah.
That's not very big.
It's not very big.
It's quite small.
It's quite small. But there's a lot of galaxies.
There's a lot of galaxies. Okay. Yeah. So this is not sort of, let's find all the galaxies in the sky. This is, no, we're going to just look at this little bit, this tiny bit of the sky and count as many as we can.
Yeah.
Yeah.
So what you do if you want to measure the spectra of lots of galaxies is you can set up it's like a plate. And you drill holes in your plate at the positions where you expect the galaxies to be, and you put a special little optical fiber underneath all of those holes, and that catches the light from that particular galaxy, sends it to a spectrograph, and you can kind of take, dozens to hundreds of spectra at a time.
So it's what you're saying is you're just collecting just the light from the places in the sky where you know that there are galaxies there, or you expect that they're there, and so you're blocking everything else out. Just go, no, just that bit, just that bit there. Right.
Yeah. So that was a really revolutionary technique. So the 2DF survey was done on the Anglo-Australian telescope, which is now called the Australian Astronomical Telescope.
Yep. Kept the acronym, changed the name.
Yep. And it was really famous. It was a wonderful survey when it came out. They looked in two different directions, kind of polar opposites, above and below the plane of the galaxy, just to get rid of all the junk that's in the galaxy.
Yep.
Didn't want all that. And they made an amazing first map, which is where we kind of got the first idea about this whole filaments and voids and walls and foaminess. And it was just a fantastic...
So that's where that came from. And that was, you said in the 90s, did you?
So early 2000s were the first publications coming from that. And then, of course, we wanted to do that and do it bigger and do it better. So we also now have what's probably the most famous galaxy survey. It's the Sloan Digital Sky Survey.
Yes, again, heard of that one.
Yeah, so this is Sloan is a 2.5 meter telescope at Apache Point Observatory in New Mexico. And what they have been working on for a very, very long time. I mean, the last really huge data bundle release that they were doing in this part of the project was in 2009. And they took the spectra of 4 million objects.
Wow. And over what kind, like how much of the sky is that one looking?
So the whole Sloan Sky Survey, it's about 35% of the whole sky.
Right, so that's a much bigger slice.
Yeah.
And they're looking at millions of objects, tens of millions of objects.
Yeah, so they did both spectroscopy and photometry. So they did the spectra and they did these redshifts using very precise measurements. So they did that for about 4 million objects. But they also did some just photometry, some brightness measurements and color measurements and basic filters. And they did that for 1 billion objects.
Wow.
So it was a massive, massive project. And, you know, the Sloan Digital Sky Survey is famous for lots of things. We've done Galaxy Zoo is one of the famous outputs from SDSS. You know, it's just huge. It's one of the, I think, the most ambitious and surveys that we've ever done. At their height, at their peak, I guess, they're producing something like 200 gigabytes of data per night.
Good God. It's just off the charts, isn't it?
It's amazing. I love it.
But I mean, no wonder this kind of work, you know, had to wait until we were actually capable of not just seeing these things, not just gathering the information, but then dealing with the information. You need the computers and the networks and the artificial intelligence, you know, the algorithm sitting in the background going, what are we looking at on this massive scale? That's just nuts.
And so again, they saw these very same structures, and we got more nitty gritty into the filaments, the voids. How big are they? Why are there's walls over here? What are they? We're still naming some of these things. You know, we got like the Great Sloan Wall, which is named after the Sloan Survey. It's a Sloan telescope. So yeah, it's really, really cool. I think my favorite output of the whole project, which came out a couple of years ago, is, and we'll put a link to this in the show notes, is they've got a 3D fly-through.
Oh, yes, I remember seeing this when
galaxies.
It came out.
Which
is
amazing.
Awesome. That's so cool.
Yeah.
That's so cool. Although it does then really bend your brain to, as you're having a look through that. And do, like listeners at home, go and follow that link and have a play with it. It's great fun. But it then does bend your brain a bit to think, hang on, what's the scale of this? How fast am I moving as we're flying through this thing? It's just bizarre.
Yeah, and each of those galaxies, and there's heaps of them whizzing all around you, has, billions and hundreds of billions of stars and planets, and, it's all very, really big scale stuff. You
feel a bit like a god doing that. It's really quite amazing. So is there any sense from all of this? Like, this is mapping it all out. This is saying what's out there and where is it, which is amazing enough in itself. But are we getting a sense for, like, I mean, you said before it was down to sort of the quantum fluctuations and the dark matter, but are we getting any better of a sense for how and why are these filaments and walls and voids structured? Like, why have an enormous void? Why have a wall? Why have a filament?
Yeah, so it is one thing to go out and make the observations, and they're amazing, but you also want to understand those observations. What are they telling you? And so we can't just kind of push the rewind button on our universe and kind of watch it go in reverse and say, well, what are the steps between day one of the universe and day to day? So what we do instead is we use simulations and models to do that. And the goal of doing the models is that you can input what you think is the correct set of physics, push play on your model, come back in 13.8 billion years of your model's time, and see.
Hopefully, it's running in more than real time.
Yeah, or much faster, and then come back and see. Well, is what it makes at the end the same as what we see around us today?
Yeah.
Have you recreated the universe?
Does it look right?
Yeah.
And those models, I would assume, they're not modeling the actual universe. They haven't got everything in them down to the level of, planets and people wandering around and atoms. They're dealing with, their fundamental structures would be much bigger than that. I would guess that they would be dealing with, their smallest grain structure in the model would be what, maybe clusters or galaxies or...
Well, it's amazing, actually. I mean, I'm sorry if I'm not going to mention your absolute favourite simulation over the next bit of this podcast, because
You're talking to me or the listeners?
The listeners. I mean, there are lots of these, and maybe you've got a favourite as well.
I don't think I do.
But there's lots of these massive supercomputers, and they call them runs. Like every time you make a universe and you go from 0 to now, then that's called a run.
That's
and
a run.
Yeah.
Yeah.
Now, those runs are extraordinary. I mean, these are not kind of you put a few particles in a box and push the play button on your laptop and see what happens. I mean, the most famous, I think, one of these runs, if you like, is called the Millennium Run.
Ah, yeah, I have heard of that one. Yeah.
So this was run where they took... I've got the numbers actually here. So it was they took a cube, and they took this cube to be 2 billion light years across on each side. So
That's a significant chunk.
it's a chunk of the universe. And they put into that cube about 10 billion particles. Now I'm going to use particles in air quotes here because they're not actually...
They're not protons, neutrons,
No.
photons.
Each of those particles is about 1 billion solar masses.
Right. Okay. So it's, but 1 billion solar masses. So we're talking chunks of galaxy size particles. Yeah.
So all up then it ended up with something like 20 million galaxies that you were looking at, to try and form in your run, because you start from very smooth stuff and then you try and recreate structure.
Right.
Now that is incredible because, I mean, on a very basic level, you've got to calculate if you're only doing gravity, only gravity is the thing that's going to make the universe evolve, then you've got to calculate all the gravitational interactions between all of your, 10 billion particles to all the other 10 billion particles.
That's nuts. That's absolutely nuts. I mean, so that's how these simulations work, right? Is that your feed in at time 0 is, let's put all these particles in here, and maybe you put them in a particular distribution, or maybe you just spread them out randomly or uniformly or whatever it is. But we've got all these lumps, and those lumps are defined by their mass, presumably, maybe their size, although I don't know whether physical size is important on that scale. Let's just assume they're defined by a couple of small parameters. But it's not, this is made of this stuff and it's got human beings in it, and so it's just a lump. And then they're also defined by what are their interactions. And if it's just gravity, then gravity says, well, this lump influences and is influenced by all the other lumps around it, even as far as across the other side of the simulation, like extraordinary distance away. But if you've got that many lumps, they're all talking to each other, then you advance your simulation forward one time step, and you do that calculation again, and you give another time step, and you do that calculation again for all of those. Wow.
It's a lot of number crunching you've got to do.
That's
and this
crazy.
Is why we need supercomputers to do this.
Yeah.
Because, nothing else is really just going to cut it. So the Millennium Run was run on a supercomputer in Germany, and it took a month to run. So imagine, pushing play on your code and then coming back 1 month later. You better hope there's no bugs in there. It took 25 terabytes to store the output.
Good Lord.
And this was in 2005. So this is
That's crazy.
a wee while ago now.
That's crazy.
Where 25 terabytes wasn't just kind of, just chuck together a few
Can't just go and
hard drives.
buy that down at your local electronics shop. That's, okay. And so what were the results of the Millennium Run?
So the results of that run basically said you can create structures that look almost identical to the things that we see around us today, but only if you have dark matter.
Right. Okay. So this is where we come back around to, you're going to need dark matter in there, which is, like, we keep coming back to this, Emily. There keep being things in the universe where this only works if we have dark matter. Yeah. And have we figured out what that is yet? No.
But if it's one of the things, if I can just really convince anybody, is that dark matter is there. We know it's there. We've measured it so many different ways.
On so many different scales.
Because it feels like it might be just kind of this nebulous thing that you could just, if you wrote your equation a little bit differently, if you did your measurements a little bit this way, or you corrected for this particular thing, then it would go away. It's not going away.
It's
really
going away.
not.
It's there.
It's a real thing.
Somewhere, but we
dark
don't know.
energy, I'll have that conversation with you about. But dark matter, no, it really is a thing. It's there. We just don't know what it is.
If only we could figure that one out.
So these simulations obviously have evolved over since the Millennium Run. So a couple that I will mention. One's called the Bolshoi supercomputer simulation. So this was in 2010. This was probably still one of the most accurate cosmological simulations. So they had an amazing amount of new data that came out of that one. One of my favorites that I looked into quite a lot was called Illustris. And Illustris ran, well, these things are kind of like onwards. So when I say like 2010, it's kind of onwards. These, you run your first things, you put out your first few results, but then you're constantly improving on your code and your models and things like that.
I can imagine that tweaking would be just by itself.
So the Illustris simulations run, so they started in 2017. They've been running a few more since then. But they include not only kind of this idea of gravity, and not only the idea of that your gravity makes kind of structures, but then they talk about in their models what happens when you start to create things like galaxies, and what happens when you evolve galaxies and have stellar evolution processes happen within those galaxies.
Oh, I see. So these aren't just static lumps of stuff now. They're changing and evolving lumps of stuff.
Yeah. So you've not only got particles, which are your kind of, in this case, stars and things like that. You've got gas, which is kind of being recycled through galaxies. So you have to have gravity. You have to have hydrodynamics for your gas. You have to have chemical processes. So this is, you've got stars that are going through nuclear synthesis, so that changes the chemical makeup.
Wow, it's down to
your
that
galaxies.
level.
Yep, you've got radiation.
This is almost getting to the point of, no, we're just going to actually literally simulate the universe now.
Well, exactly. And then what really started to floor me was you've got magnetic fields in there as well.
What?
And magnetic fields are hard.
They are hard. I mean, it's hard enough doing the gravity, let alone throwing in all the chemistry and stuff and the hydrodynamics. You're going to throw magnetic fields in there too?
I know. It's amazing.
Who are you people?
Yeah. And so you're modeling the evolution of the universe, including the evolution of galaxies in that process, which is just stunning. So the original survey, which is still sort of ongoing, simulation, started off in a supercomputer that was, several supercomputers that was run in France, Germany, and the US.
And sorry, which is it? This is did you say this is the Illustris?
This is the Illustris survey. So the largest run that they ran it over, the original one ran over 8,192 cores. Wow,
8,000 cores. That's okay. That's big.
I mean, I've got 8 in my computer. That's a few.
Yeah.
The whole thing had 25 terabytes of RAM.
Mm-hmm.
If you're a computer nerd, that's a lot. That's quite exciting to have that. It took 19 million CPU hours. So what that means is you've got your standard CPU in your computer. So you've got your PC. You're sitting there doing some stuff. It would take you on your single CPU 19 million hours to run this.
Fortunately, they had quite a few processors available. Even so, how long did it run? Is it running?
I don't actually have the full time that it took to run in front of me, but yeah.
A long time.
Yeah, a while.
Wow.
So if you were to sit down and just push play on your own kind of personal computer at home, it would take you on the order of 2,000 years. To run your survey simulation.
And sorry, has it finished? Have we got results from that, or is it?
Yeah, we
still
do.
going?
Yeah, so these are some of the most detailed parts of these kind of simulations. So smaller areas, but you've really got details of the interactions between galaxies and the evolutionary processes in those galaxies, so they're beautiful. The outputs of these surveys.
They must be stunning. And I'm guessing that at this point they're basically saying, "Yep, we get what we see."
Yeah, but you can do a lot of tweaking with your models and sort of get lots of information out, which is why it's still important to keep going with these things. I mean, the 2018 run, I think, of Illustris had something like 25,000 cores going on it. So, computing power is growing, our ability to do stuff is growing. And what's super exciting, I didn't read a lot into this, but there's a new kind of type of simulation that's starting up now, which is called using artificial intelligence. So this is using the idea of machine learning that, machine learning is exploding into science. We are using it to handle big data, to handle big simulations, because you can teach computers to figure out how to effectively write the code that they need themselves.
Yeah. So I'm trying to figure out where the machine learning would be valuable here. Is it that, like, as these models get more and more complicated, and just to be clear, just doing gravity alone is hard, but as they get more and more complicated, you're getting more and more parameters being put in here. There are more things that you can fiddle with and tweak, and what if the magnetic fields are more important or less important? What if this is more important, less important? And that's really hard. It's almost an impossible problem because there are so many dials you could turn to find, well, what's real. And machine learning is really good at saying, let's not worry about that. Let's just look for patterns. Let's find solutions that work by sampling a lot of different things and learning from, if we go in this direction, that seems to be improving. Is that the kind of idea that we're talking about?
It is, yeah. And one of the great things you can do with machine learning is you can say you've got a problem like the evolution of the universe, where you've got, let's say, 100 different parameters you can tweak. Now, you could tweak, things like the amount of dark matter, when it's, when collapse starts to happen, the strength of different magnetic fields, whatever those parameters might be. Now, if you've got to tweak, our old process would be kind of, okay, let's just move each one of these individually and see what happens. But it's really hard to figure out, if you're moving 3 or 4, how does that affect another 4 or 8, let alone 100 different parameters. What artificial intelligence and machine learning is really good at is spotting, actually, you might not need to move all of these 100. It turns out that if you move this one, it actually affects this other one. So you can kind of combine those into a super parameter. So you don't need to individually look at all the individual things and actually, hang on, this parameter over here turns out to be totally unimportant, so let's just forget about that. And so it can make these links, which physicists might not notice, because you might not necessarily think that those two things are linked, but you can reduce down your parameters to a much more manageable kind of space and actually figure out which are the important ones and which are the ones we need to look into.
Goodness. So are we anticipating, like, are there any big runs or any big simulations going on that we're kind of holding our breath to see what happens next?
So one I found, which I found really exciting, and this is, again, a wonderful name. This is called the Dark Emulator.
Ooh. Sounds exciting.
The Dark Emulator, which is a piece of machine learning to do this. It's running, the 2020 is when they're doing work on this right now, basically.
Yeah.
You can run this on a laptop.
Wow. Okay.
That's the power of machine learning, is that you don't need necessarily. All those other simulations and surveys will continue because they're doing specific things with the data that they have, and you need that even to input into machine algorithms.
Yeah,
right?
Machine learning isn't magic. It's still operating on knowledge that we have. And so we need that knowledge. We need the physics. We need the data for the machine learning to then find the patterns.
Yeah, but this is just a way to take a different direction and maybe get some different results that might then feed into further big simulations as well.
Awesome.
Yeah, it's really, really exciting.
Well, that took an unexpectedly slightly computer nerdy turn at the end there, but why not? Why not start talking in terms of, terabytes of data and gigaflops and so on? That's always fun. Listen, Emily, if people wanted to contact us, if they had a question or a comment or anything at all, just wanted to say hi, how would they do that?
So if you've got just a few characters that you want to throw your characters our way, then we are at SyzygyPod. That's SYZYGY pod.
That's right, on the Twitters and other social media as well. Other social media are available.
I saw you call us Syzinstagram.
I was working on that one, on the website.
I can't quite say it yet.
I don't know. Maybe I'll correct
it.
I
like it, but I just can't say it.
Can't say it. Which, for a piece of marketing is probably bad. Syzygy is bad enough, but let's not go making it worse for ourselves. Yes, we are on Twitter, we're on Instagram, we're on Facebook. Just go and find us as SyzygyPod. We're out there. We also have a website, syzygy.fm, where you can find all the past episodes, all the show notes, all the pretty pickies, and a contact form so that you can say hi.
And Chris has been working really hard to make the website even more beautiful.
It's nice and pretty.
Lovely.
It's pretty.
And if you want to see some Great Wall... I had another peek at our Great Wall.
That's right. We have our own Great Wall, which is the Great Wall of Gratitude. All of our supporters and all of the people who have just, whether it's throwing a bit of in-kind support, like the University of York in just basically employing Emily, through to people who are patrons from our patreon.com account, all get their thanks up on our Great Wall. Their names go up on there. So if you too want to be on our Great Wall of Gratitude, then you can go to patreon.com/SyzygyPod and sign up to be a supporter of the show. Whether it's $1 or more every month, it helps to keep the electrons flowing and the lights on back here at Syzygy HQ. The other way you can support us is just by spreading the word around. Tell everyone you know that there's this awesome thing called the universe, and you should learn more about it by going and listening to Syzygy. That would be great. Leave us some reviews, leave us some stars on your podcast catcher of choice. It helps us to rise up through the noise so that more people can share in the wonder of the universe. Speaking of wonders of the universe, we'll be back again in about a week or so with some more cool stuff. So we'll catch you then. See you later, Emily.
See you later.
Bye, everybody.